Hello class. Alright, today we're going to do a review of this week's class, which was Monday, March 3rd. So March is 3.3.3 and 3.5, which essentially was all of Chapter 7. Chapter 7, which is a structure and synthesis of alkenes, which essentially I'm just going to say alkenes. So the topics that we're going to talk about, there's not a real lot of topics in Chapter 7. It's kind of short, but the few topics that we do have are relatively important because Chapter 8, addition reactions, reactions of alkenes, come directly from the Chapter 7 stuff. So the first thing we're going to talk about is nomenclature of alkenes. We're going to build on and add on to the alkane and alkyl halide nomenclature system we already know. We already know the RNS nomenclature system, which is for chiral centers. We also know that alkenes can be cis or trans, but now we also have an EZ requirement that we can put on these alkenes. So we'll talk about that. I'm going to skip over heats of hydrogenation for this lecture. I just don't find it that important. I mentioned it in lecture because I just kind of wanted to point out that different alkenes have different stabilities, i.e. Zaitsev's rule. But I'm going to go past it. The things I want to focus on in this chapter or in this lecture review are going to be dehydrohalogenation, dehalogenation, and dehydration, specifically dehydration of alcohols. There's other things you could dehydrate, but we're going to do. So these are essentially our three alkene methods. They're all elimination mechanisms that we talked about before. Right? So they're all either E1 or E2, and we're going to take a look at them a little bit more in detail. So we got nomenclature, those three mechanistic types, and then we have a new thing, the Hoffman product. And so that's really Chapter 7 boiled down to what I think are the important things. So without further ado, let's get started. Nomenclature. Right? Naming alkenes is the same way that you name alkanes and alkyl halides, only now you have to count the double bond. So we'll start with a very simple one. To name the alkane, you do same as alkane, but then you drop ANE, because you're no longer talking about an alkane, you're talking about an alkene, and so you add ENE. If you have more than one, such if you have two, it would be di, 3 is tri, 4 is tetra, etc., etc. And of course, you need to specify with a number where the actual position is. So if I just give you a molecule that looks like this, right, the IUPAC system would say that I count 1, 2, 3, 4, 5, or I could count 1, 2, 3, 4, 5. I should always count so that the substituents are at the lowest numbers. In this case, the substituent is not necessarily a substituent in kind of the classical sense, but it's part of the chain itself. So I should count 1, 2, 3, 4, 5. The old IUPAC system would call this 1-pentene. But the new IUPAC system, which I actually prefer, although I will accept either answer on a quiz or exam or anything like that, would be pent 1-ene, because the ene, which is the alkene, is at the 1 position. It starts at the 1 position. And that's why I like the new system a little bit better. If we did this structure, we had like a ring, we should count such that the double bond is at the first number in the ring. So I would count 1, 2, 3, 4, 5, 6. So the new IUPAC system would say that this is cyclohex 1-ene. Okay, so those are relatively easy. What if we had something like this? Okay. So now we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we still get 5 as the longest chain, but we want to count such that the double bond is included in that chain. So we can either count 1, 2, 3, 4, 5, or we could count 1, 2, 3, 4, 5. Using the same rules that we learned before, always number so that the substituents are at the lowest number. We should count 1, 2, 3, and then it doesn't matter if we count 4, 5 here. That's the exact same thing as if we were to count 4 or 5 here, because they're both ethyl groups. So in this case, it actually doesn't matter. Okay, so what do we have? At the 3 position, we have an ethyl. Our main chain, so at 3 position, we have an ethyl, which is this. Our main chain is 5 carbons long, and the double bond is at the 2 position. So we have pent is our main chain. Where's the double bond? It's at the 2 position, so pent-2-ene. And what do we have at the 3 position? We have an ethyl group. Let me just get this out of the way so I have room to write. So we would say 3-ethyl pent-2-ene, right? And there should be no spaces here. That's just my bad handwriting. There we go. Cleaned it up. 3-ethyl pent-2-ene. All right. We said before that double bonds can be geometric isomers, so they can have cis or transness. So if I had something like this, if I just say 2-butene, using the old IUPAC system, or but-2-ene, that's actually ambiguous, right? Because it doesn't specify whether I'm talking about this molecule or this molecule. This name, as it's currently written, doesn't explicitly appeal to one of these particular molecules. So we say that this one would be the trans version because there are exactly 2 groups attached. So it would be trans 2-butene or trans but-2-ene, and this one would be cis 2-butene using the old IUPAC system, or cis but-2-ene using the new IUPAC system. So that's fine because we have exactly 2 substituents attached, 2 non-hydrogen substituents. But what happens if we have more than 2 substituents, right? So suppose I give you a structure that looked like this. Okay. Why did you do that triangle? There we go. Okay. Now our longest chain can be 1, 2, 3, 4, 5. 1, 2, 3, 4. Can't count here because this is part of the ring. 1, 2, 3, 4. 1, 2, 3, 4. The longest chain should be counted 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. We always count so that it puts the substituents, the highest priority substituent, at the lowest if there's a tie. So 1, 2, 3, 4, 5. So again, we're talking with a pentene, specifically a pent-2-ene. Oops, I'll scoot this over a little bit. Pent-2-ene. And what do we have? At the 2 position, we have a cyclopropyl. So we have to put that somewhere in our name. And at the 3 position, we have a methyl. Right? And now we also have to worry about the organization of this, right? So first let's build the name. C for cyclopropyl comes before M for methyl. So it should be 2-cyclopropyl. We're still using alphabetical. 3-methyl pent-2-ene. However, if I just give you this name, 2-cyclopropyl, 3-methyl pent-2-ene, you could draw this structure, or you could also draw this structure, right? Because that would be 1, 2, 3, 4, 5, 3-methyl, 2-isopropyl, cyclopropyl, pent-2-ene. But these are not the same as each other, right? There's no way I could take this molecule, pick it up, flip it over, rotate it, do whatever, such that it completely overlaps with this molecule. These are 2 separate structures, 2 separate molecules. So what is the relationship between them? Well, because we no longer have exactly 2 groups, we can't use the cis and trans nomenclature. And so instead, we have to use a new system, which is called the EZ system. Okay. Using the EZ system is easy, right? Here's how you do it. First thing you do is you chop the double bond. So chop the carbon-carbon double bond in half, so that you're only looking at exactly one side. So let's do this one. I'll draw a dotted line to say this is where I'm going to chop. Now I compare groups. So step 2 is compare groups on a given side. So I pick one of the sides of the double bond. It doesn't matter. I don't know why. I got to recalibrate this pen. This is so annoying. Right? I pick one of these sides. It doesn't matter. I'll pick this side. And I'll say I'm going to compare a methyl group to a cyclopropyl group. Right? And I use the RS priority system, the Kahn-Engold Prelog priority system, to determine priority. Priority, right? So I say what's attached. We have a carbon and a carbon. That's a tie, so I go one atom out. I have a hydrogen, a hydrogen, a hydrogen. So I write that down. Hydrogen, hydrogen, hydrogen. Then I go to this atom. What's attached? A carbon, and a hydrogen, carbon, carbon, hydrogen, CCH versus HHH, the H's cancel, C beats H, and so this is a higher priority group, so circle it. Then I do the same thing for the other side. Step 3 is repeat for other side. Okay, I go to this carbon, I go to this atom, I have a carbon, I go to this atom, I have a carbon, so that's a tie. So I go one atom out, hydrogen, 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 write that down because I can't remember things. I go to this atom, I have a hydrogen, and a carbon, so I write that down, hydrogen, hydrogen, carbon, hydrogen ties with hydrogen, hydrogen ties with hydrogen, carbon beats hydrogen, therefore this is the higher priority group, circle it. Okay, step 4 is to actually do the assign E or Z. You take the two groups that you circled, this is why we circle them, and you say, are the two groups that I circled trans to each other, meaning they're opposite of each other? If so, you have the E isomer. If the groups are cis to each other, so the cyclopropyl is higher priority, and the ethyl is higher priority, so this one would be the quote-unquote cis version, that means it is the Z version, which means they're on the same side. Right? So technically, this molecule on the left would be, I'm out of space, of course, would be E2, and the E goes in parentheses, cyclopropyl 3-methyl-pent-2-ene, and this one would be Z2 cyclopropyl 3-methyl-pent-2-ene. Okay. These words come from E stands for the German word for entgegen, my favorite German word, which just means opposite, and Z comes from zusammen, the German word, which just means same. Right? So they're just they're German derivatives because we're English and we steal things. So we use the EZ system when we have more than exactly two groups attached. If you only have one group attached, like in my original example, right? There's only one group attached here, specifically it's a propyl group on position 2. There's only one way you can do that. So pent-1-ene is as explicit as you need to be. Same thing here. If I have cyclohexene, there's only one way you can draw a cyclohexene, and so one cyclohexene or cyclohex-1-ene, or even just cyclohexene are all acceptable. I think the 1 is redundant in the IUPAC system. Okay. Only when you get more than two groups attached do you have to use the EZ system. Right, so sometimes I like to ask questions like, is this E or Z? But then I give you something that only has two groups. So the answer would be neither, cis or trans. Right, let's take a look at this one. Right, we got chlorine, carbon-carbon double bond, bromine, hydrogen, and methyl. Okay. What is the name of this one? Go ahead and pause the video and solve this right now, and then I'll do it for you. Alright, let's see what you got. So first step, chop the double bond. Then compare each side. Bromine versus chlorine, who wins? Bromine's a larger atomic number, so bromine wins, so circle it. Compare carbon versus hydrogen. Hydrogen's always a loser, so methyl's higher priority. So is this going to be E or Z? These are opposite each other. They are not on the same side as each other, so they are entgegen. So this is the E. So we've determined the stereochemistry. Now we have to say how many carbons are along this chain. 1, 2, 3. So we count 1, 2, 3 such that the double bond is at the 1 position. So this would be a prop-1-ene. We have a bromo and a chloro. So 1 bromo, so that we're doing it alphabetically. 1 chloro, oops, there should be a dash there. 1 bromo, 1 chloro. Prop-1-ene. And that would be our name. E, 1 bromo, 1 chloro, prop-1-ene. Good. Alrighty, so that's how you use the EZ system. It's not terribly difficult. Let's just do one more real quick and just make sure you get it. If you can follow the rules for the RS system, you can do the EZ system with much more ease. You just determine priority using the Kohn-Angold Prelog system. That's supposed to be an isopropyl group. Okay, what does this one do? The same thing. Chop the double bond in half. Bromine beats carbon. Carbon beats hydrogen. These are on the same side as each other, and so this would be Z. In this case, the longest chain is 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So at the 2 position we have a bromo, and the 4 position we have a methyl. So 2 bromo, because B comes before M, 4 methyl, and 5 carbons long. Oops, there would be no hyphen there. Pent 2-ene. Okay. Alright, so that's our easy system. There's a whole bunch of homework problems in Chapter 7 that you can focus on to do that, and I recommend you practice those because that's an important thing to do and it's very likely to show up on a test. Here's a structure, give me a name. Here's a name, give me a structure. Or here's a name, here's the chemistry I did, what is the name of the product, right? That's a great type of question. Alright, so let's talk about our three reaction types. We have dehydrohalogenation, dehalogenation, and dehydration. So let's start with dehydrohalogenation. Halogenation. Okay. D meaning take away. Hydro meaning hydrogen. Halogen meaning fluorine, chlorine, bromine, or iodine. So fluorine, chlorine, bromine, or iodine. And ation, the act of doing it, right? So we're going to take away a hydrogen and then a halogen, and we're going to use that as a verb, so we tack on ation. Right? Dehydrohalogenation is a very common method for making alkenes from alkyl halides. So what I'm going to do is I'm going to have X, where X is equal to chlorine, bromine, or iodine. And if you notice, I didn't say fluorine this time because it turns out that the bond energetics for carbon-fluorine bonds are not favorable for dehydrohalogenation, whereas these other three are. Okay, I'm going to add Rx and a base, a relatively strong base, so I will use base with a lone pair of electrons and a negative charge to indicate strong base, and I'll end up with R double bonded to an R, right? It gives me an alkene as the product. And technically I would also end up with H base and then X minus. Okay. Alright, so that's nice and generic. Let's use something that's some real stuff. So we're going to take H, C, nope, that would make no sense, C, Br, and we do have to worry about stereochemistry now, which is why we learned Chapter 5 stuff. And this will be a methyl, and then these will just be hydrogens. Okay. So we'll start out with a strong base like ethoxide, and in one step, the rate determining step, the strong base will abstract a proton from the position that's next to where the halogen is. So the halogen is here on this carbon, so I'm going to go one atom over. I'm going to remove a proton, so I'll be making a bond between the hydrogen and the basic atom, whatever it is. The electrons between the carbon and the hydrogen obviously cannot be unaccounted for, so they have to leave and go somewhere. They're going to form a double bond. That would violate the octet of this carbon, and so the leaving group, which in this case is a decent leaving group, bromine, will leave and will give you a molecule that looks like this, which will be prop-1ene if you wanted to name it. Okay, Br minus floats around and ethanol floats around as well. That's fine. Or if you want to write it as HBr and OET minus, you could, although I like this way, it's more correct. Either way, this is what I care about, right? Do you make the right alkene? This is explicitly an E2 mechanism. So remember, when we learned E2 mechanisms back in Chapter 6, we learned that the conformation of the molecule has to be able to obtain the anti-periplanar orientation in space. So if I was here and I was looking down this bond, I would see, let me just clean up that circle because that's ugly. That's even uglier. Drawing circles is really hard. I wonder if there's like a tool for circle drawing. Sorry, I know I'm getting distracted, but I want to just... Oh yeah, that's such a good circle. Okay. Alright, anyway, if I was drawing the Newman projection and I get this, what would I see? I gotta change the sensitivity of this tip. Alright, so in the front carbon I got 3 hydrogens, so that's good. In the back carbon, I want the anti-periplanar or anti-coplanar, if you're using the language from our textbook, orientation in space. So bromine would be here, up and to the right would be a hydrogen, and up and to the left would be the methyl. So the base is going to come in, ethoxide is going to come in and grab this proton. These electrons in this bond are going to snap down, so they're going to go, that's this arrow, it's supposed to represent going behind the circle. And then when bromine leaves, it's going to take those electrons and say, peace out. and that will give you this, right? So you should be able to go from some type of line angle structure with three-dimensionality, wedges and dashes, to the Newman projection. Or if I give you the Newman projection, you should be able to go to this structure or to that structure if possible. Okay, so that's the E2 mechanism for dehydrohalogenation. If we were to do the E1 mechanism, it would look a little bit different. Okay, so let's take a look at the E1 mechanism. E1. Start with the same molecule. We'll put it in the same conformation this time, although for E1, conformation is not as important. First step in E1 mechanism is leaving group leaves. So the rate determining step says wait around until that happens. And that gives you a carbocation. It's supposed to be a 3. Okay. Whenever we generate a carbocation, we always want to ask ourselves this question. Can we stabilize this positive charge? Right? So we have to look for shifts, we have to look for resonance effects, we have to look for other rearrangements, etc. In this case, we have a secondary carbocation, which cannot get any better. If we move the positive charge to this carbon, it becomes primary. That's worse. If we move the positive charge to this carbon, it becomes primary. That's worse. So this is as good as it's going to get. So the answer to our question in this particular one is no. After we've answered that question, then we continue on with our mechanism. Then we take our base, which in the E1 mechanism would be a weak base. And so I'm going to pick a neutral molecule, like ethanol, rather than ethoxide, to be our weak base. We can remove the proton, electron snap down, and we still get the exact same final product. Prop1E. Okay. So dehydrohalogenation can occur via E2 or via E1. I'm sorry if I wasn't clear a second ago. It doesn't have to be E2, but if it's a strong base, it'll be E2 mechanisms will be promoted, meaning it's likely that it'll be E2 mechanism. If it's a weak base, then the E1 mechanism will be promoted. But for that to occur, you would need a relatively good leaving group, like bromide or iodide. If it was chloride, I would make this face. Like, not so sure. Maybe, if your substrate structure is good, like if it was a tertiary or resonance stabilized carbocation. But in general, E2, strong base, E1, good leaving group. Remember, just like in the SN1, SN2 case, we're saying, does the goodness of the leaving group outdo the goodness of the base, right? You're comparing apples to oranges. It's not a straight comparison, but you can evaluate both based on the principles of leaving groups and bases that we learned in the last chapter. All right, so that's dehydrohalogenation. Next is dehalogenation. Okay. Dehalogenation is kind of a special case of an E2 mechanism, and it specifically applies for vicinal dibromides. So I believe Carl asked in class, bromides. If there's other ways you can do dehalogenation, like with chlorine or iodine, I looked it up, I couldn't find any, so I'm pretty sure you can only do it with vis dibromides, vis meaning adjacent to. So what we're going to do is we're going to start out with a molecule that looks something like this, where we have bromines that are physically able to take on the anti-coplanar or anti-periplanar orientation in space. And we're specifically, pH stands for phenyl, which is a benzene ring. So pH equals this. And it's a big fat benzene ring. It means whatever the pH is attached to, the squiggly line, this is this. So that's what these phenols are. Right. In dehalogenation, we're specifically going to use sodium iodide and acetone. Right. It's a very specific situation. Acetone, 2-propanone, looks like that. Right. And we're going to do only the E2 mechanism. Right. E1 is not possible. E2 only. Where the iodide is going to act as a base, which is rare for us because normally iodide is a good nucleophile. It rarely acts as a base because HI is a strong acid. But in this case, it just happens to work out energetically because the size of the orbitals between iodine and bromine are favorable for bond overlap, and the size of the orbitals between carbon and bromide are not so favorable for bond overlap. And so the energetics of doing this are a little bit better than the energetics of having this, but whatever, that doesn't matter. So anyway, iodide will make a bond to the bromine, the electrons will snap down, and the bromine will get kicked out. And so we'll generate our alkene with our stereochemistry. So phenyl, carbon, double bond, carbon, hydrogen. And now, so essentially this phenyl, once the bromine gets removed, the carbon goes from being sp3 hybridized to sp2 hybridized. And so this phenyl will kind of swing upwards in the back of the page. This hydrogen will swing upwards in the front of the page to make it flat. The phenyl, this phenyl will swing downwards, and this hydrogen will swing downwards. And so we would get, in this case, would this be E or Z? Haha, trick question. This is trans because we have exactly two groups attached. So this would be trans 1,2-diphenylethyene. Okay. We also would generate IBr technically, and also Br minus, and those would just float around. And I don't care if you draw those or not. What I care about is the organic structure, the carbon. Right. So the important thing to note here is that it must be E2. It must be these conditions, nothing else. You could probably change the solvent to other polar aprotic solvents like acetonitrile or DMSO or DMF or things like that. I don't think a polar protic solvent will work, although don't quote me on that because I'm not 100% certain. So you have to have an polar aprotic solvent, and you need iodide specifically. That's the deal breaker, because this bond that's being made is the thing that kicks the whole thing off, right? So you have to have iodide present. And of course you need a vis dibromide, which means you need a compound that has two bromines that are on adjacent carbons. And of course, because it's E2, you have to be able to obtain the antiperiplanar conformation in space. Okay. So what would you get if I gave you this one? So bromine, carbon, carbon. Now I'm going to draw it a little bit differently so it's not so convenient. The way of drawing it, this structure here, where you have like two things down and then two things up, this is called the sawhorse conformation, right? Like we had chairs and boats for cyclohexane. They're just names that we give to a particular conformation just because they're very convenient and they happen a lot. Same thing here. This is convenient for ethane molecules or carbon-carbon single bonds. This happens a lot, and so we call this the sawhorse projection, or not projection, conformation. So if I say draw the sawhorse, that's what I'm talking about, although I try not to use terminology that I don't explicitly define. So if I don't draw it as a sawhorse, can you still give me the right answer? So suppose I gave you this, and we had OH. Go ahead and pause the video now and do a dehalogenation reaction with NaI and acetone and see if you can get the right alkene. Go ahead and pause. Alrighty, what did you get? You should have gotten this. H, C, double bond, C, F, H, and OH. Okay. If these are switched, you made a mistake somewhere, right? So just walk through the mechanism. I minus bonds to Br, electrons kick down, and bromine has to leave, right? If you draw it this way, it's like, well, electrons are going down, they're going back out. It looks weird. So what I would do before I do the mechanism is I would rotate the molecule. I would just redraw this part so that it's drawn in the proper quote-unquote linear way. You don't have to do this. Sometimes you can stop that. Sometimes you could do it in your head, but some people struggle with that. So let's just redraw it. So the molecule on the left, or excuse me, the carbon on the left, I'm going to draw the exact same way. So fluorine and hydrogen. Now I'm going to rotate this bond so that the bromine ends up down here. So the bromine comes around, comes out of the plane, and then goes back. So that means the wedge dashness remains the same all the time, and I'm just going to change what goes where. So if bromine goes here, then OH is going to go there, right? And then hydrogen is going to go there. Okay. So this is not sawhorse yet, right? Because I still have, 2 feet, so to speak, and 2 feet, so to speak, and I just want to have 1 foot. So what I'm going to do is I'm going to continue to tilt this just a little bit, continue to tilt that just a little bit, and continue to tilt that just a little bit in. So I can redraw this as carbon, carbon, fluorine, hydrogen. And so now bromine goes from being a wedge to being flat because I pushed it into the plane a little bit. The hydrogen goes from being flat to being a wedge, and the OH goes from being a dash to being a dash up, so to speak, and pushed it in a little bit. Okay. So hopefully you can see all those transformations. Ideally, you want to be able to do this manipulation in your head. Now when the iodide comes in, makes a bond, now we're following the exact same scheme. This guy folds up, this guy folds up, this guy folds down. He's closer to us, he's in front of the page. This one folds down, he's farther away from us, and that's how we get to that specific isomer. Is that cis, trans, E, or Z? Hopefully you came up with that's higher, so that's trans, right? There's exactly two groups, so this would be trans, and we don't know how to name alcohols, so I'm going to skip that. All right. Last one, as an example, if I gave you this molecule, and I said I'm going to do dehalogenation. Maybe I'll just write it this way. Instead of giving you Ki or NaI and acetone, I said dehalogenation. What's the answer? Go ahead and pause the video and write your answer. Hopefully after unpausing you realize that the answer is no reaction. Why? Because these are, if up is axial, up is equatorial. Right? So if one of these is axial, the other one is necessarily equatorial. The requirement is that we get anti-coplanar, anti-periplanar, and so if one is axial, the other cannot be axial in the other direction, right? Because they are cis 1,2-dibromo on a cyclohexane. So they can't obtain that periplanar, and therefore dehalogenation, no periplanar, dehalogenation is impossible, so the answer would be no reaction. Right? So that's no reaction is a valid answer if I ask for specific cases. Now, if I just did something like this, right? Suppose I said, here's our molecule, and I'm going to use a strong base like sodium ethoxide and a little bit of heat. Now we can do a reaction, right? What reaction can we do? We can do dehydrohalogenation, where we remove a hydrogen from here to kick out the bromine, and we remove a hydrogen from here, kick out the other bromine. So you could potentially get this, or under extreme circumstances you can actually force it to be an alkyne, and we're going to learn about that in chapter 9 where you can get that. This is a weird one, but so don't worry about this, but potentially you could do this if you have strong enough base and you have enough heat. So alright, so that's it for dehalogenation. The last topic is dehydration. Specifically dehydration of alcohols. Right. Alcohol dehydrations are something we essentially already know, right? But we don't know that we know it, right? We already know that our E1 mechanism, in general, goes like this. Carbon has a leaving group attached. Leaving group says, you know what, I'm sick of you, carbon. You don't treat me right. You don't brush, you don't wash the sink. You don't do the dishes. I'm out. Positive charge. Then some weak base comes along and says, well, I guess I'll be a base. Weak bases are always sounding like Eeyore in my head. I don't know if that's true for you guys too. And you get an alkene, right? That's our generic E1 mechanism. Dehydration of alcohol is the same thing, only our leaving group is not inherent in the molecule. We have to trick it a little bit. So what we're going to do when we do a dehydration of an alcohol is we're going to start with an alcohol. That's just a carbon with an OH group. And I want to put that OH group down here so that I have analogies. So we have this, right? OH is not a good leaving group, right? If OH leaves, right, if this happens, what would you get? You'd get carbon with a positive charge, and you get OH minus. What do you think is going to happen if OH minus leaves a molecule and therefore is in close proximity to a positive charge? Hey, you're negative, I'm positive, let's attract. And the backwards reaction happens. So this equilibrium does exist. It just exists so strongly in favor of the alcohol that we basically don't even think about it anymore. We say, that's not a real thing to consider. Let's only worry about, real chemistry. Okay. So with dehydration of an alcohol, what we're going to do is we're going to add some type of strong mineral acid like H2SO4 in heat. We could also use H3PO4 if you're in lab. We did this yesterday. You can use HCl, you can use HBr, you can use HI. If you remember that list of 7 strong inorganic acids, HClO4 from Gen Chem, right? If you remember any of those, you can use any of these, right? Anything that's strong enough to protonate this alcohol, right? So any of those guys. I'm just going to sum up all of these guys, and I'm just going to write it as H3O+, because all of these are going to be dissolved in water, which means you're going to have hydronium, H3O+, floating around, and it's just easier to draw that way, and I don't have to worry about keeping track of the sulfate or the phosphate or the chlorate and all that junk, right? So the first step in the dehydration of alcohol is protonation of the alcohol by some strong acid. That gives us structure that looks like this. Okay. Now we've gone from OH minus, which would be a terrible leaving group, to water, which is a neutral molecule, which is a good leaving group. And so water will pick up and leave and say, I'm out. I'm going to go hang out in the ocean with all my buddies. And you get a carbocation. So same thing in the E1 mechanism, same thing here. Again, whenever we generate a carbocation, we should ask ourselves the question, is there anything we can do to make this carbocation more comfortable? We care about carbons, we care about his comfort, and we say, can we resonance stabilize you? Can we shift you? Can we rearrange you? Can we do something to make your life better? In this case, because I didn't draw anything else in the molecule, the answer is no, there's nothing to worry about. We'll cover an example where that is an issue later on. So then we form a carbocation, then something in solution acts as a base. Hey look, we just generated water, why don't we just use water? So water, perhaps, or it could be the conjugate base of one of these acids. It doesn't matter. We'll grab the proton, and you form your alkene. Right? It's the exact same alkene. So dehydration of an alcohol mechanism, essentially we already learned when we learned it as E1, only now it's a specific case where the leaving group has to be treated with a little bit of acid first to turn it into a good leaving group. Right? It goes from like leaving group alpha to leaving group prime. And then leaving group prime can actually do the thing that leaving groups do. Alright, so let's look at some simple examples. Here's yesterday's example from lab, if you were in lab last night. We took the alcohol. We used sulfuric acid and phosphoric acid. But in my example here on my notes, I used hydrochloric acid. And we have to add a little bit of heat, because remember, heat indicates that elimination reaction is likely to occur. So the alcohol gets protonated to give you good leaving group, which is water. Water says bye-bye. Carbocation. Is there anything we can do to that carbocation to rearrange, shift, resonance stabilize, etc. to make it more stable? No, because it's secondary and all the other carbons in the atom are secondary. So all we can do is remove a proton from one of the positions next to it. I will use water to do that. No, I'm gonna use chloride this time, Cl-. Right? It's not a good base, but it's a completely valid reaction. And that gives you your final product, cyclohexene. And technically it would give you HCl, so it regenerates the acid. The acid is a catalyst in our dehydration reaction. Right, if I change the game slightly and I toss on a methyl group, I really need to change the sensitivity of this pen. It's annoying because my PDF annotator program that I'm using to write this, I should say, wasn't acquired through the normal means, and so it's a little buggy. So I always have to, like, every time I plug it in and start it up, I have to like redo a bunch of crap to get it working. So again, we're going to use strong mineral acid. We're going to use a little bit of heat. First step is protonation of the alcohol by the acid. I don't want to draw out sulfuric acid because I'm lazy, and so I'll just use hydronium. That's completely acceptable because we have, whenever you have an inorganic, Oh, yeah, see what I was talking about? It's a little buggy. So whenever we have a strong mineral acid, we also have water. That will give us this structure, OH2 with a positive charge. Water, being the good leaving group that it is, says, you know what, I'd rather be on my own. I'm moving out, Dad, and I'm not paying rent anymore. Leaving you with a carbocation. Is that carbocation? Is there anything we can do to make it more stable? No, it's tertiary as it is, right? So if we move it here, it'll be secondary. If we move it here, it'll be secondary. If we move it here, it'll be primary. And so it's as stable as it's going to get given this particular structure. Then the next step is to use something in solution as a base, could be HSO4 minus, it could be SO4 2 minus, or it could be water. It's more likely to be water, honestly. Water, remove a proton. But now there's a couple choices, right? You can remove a proton from up here, or here. Or you can remove a proton from here or here, right? So these 4 protons are all the same as each other, right? Because the molecule is symmetrical about this axis. But this proton's different. So if water removes one of these guys, you get the major product. That's ugly. Let me redraw that. You get the major product, the Zaitsev product. And if water removes one of these protons, you get the minor product, which does have a name. We're going to cover that in 1 second. Okay. Hopefully that mechanism makes sense. You guys really need to know mechanisms, because I guarantee on the test I'm going to say, here's a reaction, show me the mechanism. Let's change the game a little bit. So now we're going to move the alcohol. What am I doing? I don't know why I can't draw today. I didn't drink enough coffee. We're going to move the alcohol over 1 atom. So before we had the alcohol here, now we're going to scooch it over 1. And I'll just throw a different acid at you just so we get in the habit of using different things. First step is protonation of the alcohol. Right? This is what you want to do when you do these problems. You just want to be able to talk yourself through the mechanism. So the alcohol gets protonated. Remember, the arrow goes from electrons to the target, and the electrons in the oxygen-hydrogen bond have to be accounted for. They can't just float around in space. That gives us our water, which is a good leaving group. It's okay if you draw it like that. I'm okay with that. I'm also okay if you draw it with this. Although, honestly, I would prefer that you draw it like this, but if you do it the way that I did with OH2, that's correct as well. Water leaves. You do have to have this bond, though, so make sure you have that. That gives us a carbocation. Again, whenever we generate a carbocation, what should we ask ourselves? You should be muttering to yourself, is there anything we can do to make this carbocation more stable? The answer is yes. The answer is yes, right? Sorry I shouted. I get excited when I get to do shifts, right? So, because this is a secondary carbocation and it's adjacent to a tertiary carbon, that is what clues us off to say, aha, we can indeed do something. This carbon has a hydrogen, and so if the hydrogen takes its 2 electrons and scooches over and bonds to that carbon, this is called a hydride shift. Hydride is H with a negative charge, right? So we're taking the H and we're taking both electrons that are in the bond, right? We're taking both these electrons. That's what makes it a hydride. The resulting structure then, sorry, that positive charge is ugly, looks like this, right? Is this primary, secondary, tertiary? This is tertiary, so it's more stable. That's why this happens. So ask yourself the question. If the answer is yes, then go ahead and do the shift, the rearrangement, the resonance, whatever it is. Now water will come in as our base and remove a proton from either this position or this position. And again, you'll get the same 2 products. You get the major product, which is the Zaitsev product, or you get the minor product, which is not the Zaitsev product, and we'll talk about that in a second. What structure can you not get? You cannot get this structure. No. Okay. I want you to just pause the video real quick and think about how you would get this structure and see if you can come up with the reason. So go ahead and pause. Alright, so the reason you cannot get this structure is because in order to get it, you'd have to remove a hydrogen from this position right here so that the electrons go here. That would be this double bond. That does not happen because as soon as the secondary carbocation forms, it immediately turns into the tertiary carbocation because that's a step down in energy. So water does not have the time required to act as a base and remove this proton because as soon as this happens, it goes and it jumps right over to the tertiary. I don't know if it makes a slurping sound. I actually haven't heard molecules in a while, so but that's how it sounds in my head. So that's why you can't get this structure, and you necessarily only get these 2 structures. Okay. So hopefully you understand that, and of course you should be able to name these molecules, right? This would be 3-methyl cyclohexene. This would be 2-methyl cyclohexene, or 2-methyl cyclohex-2ene, and then don't worry about this one. This is exocyclic, so we're not going to name exocyclic double bonds. Alrighty, the last topic of Chapter 7 is called the Hoffman product. 2 N's. Okay, the Hoffman product is essentially the least substituted alkene. Right? So what we've been doing up to this point is we've been saying that the major product is the Zaitsev product. Well, that's not completely true. I kind of lied to you a little bit for the purposes of helping you understand it. Now that you hopefully understand the Zaitsev product, you understand E1 and E2 mechanisms, now I can go back and say, well, actually it's this way. So for example, consider this molecule. This is the exact same one I used in lecture, by the way. Right? There are two hydrogens that are alpha to this bromine, or they're one carbon over, right? There's a hydrogen, I think I actually want to draw it up here. Okay, there's this hydrogen and there's this hydrogen, right? If this one gets removed, I get the alkene here. If this one gets removed, I get the alkene here, right? So in the presence of a strong and small base, like ethoxide with ethanol as a solvent, a small base, so this would be small base, a small base will remove the hydrogen that gives you the most substituted alkene, right? So essentially it gives you what we're going to call the Zaitsev product, or what we have been calling the Zaitsev product. And what is the Zaitsev product? Okay, and you should be able to name this as well. So this is a Zaitsev product, and in this case, it's the major product. The minor product then would be the less substituted alkene, which would be this molecule. Okay, meaning a double bond goes here. This is minor, just like we said. And the name of this one, the less substituted alkene, is called the Hofmann product. Right? So with a small base, the normal rules of elimination chemistry applies, and the Zaitsev product will be the major product. So that's no change as to what we've talked about. But, and it's a big but, and I'm not going to lie. Hope you guys like that joke. If we don't use a small base, and we use a bulky base or a fat base, okay, take the same molecule. The word is bulky, technically. I like to use fat because I find it funnier. Yeah, I'm a fan of Chris Farley. If we have a big base like T-butoxide, right? T-butyl group with an oxide negative charge, and it could be in solvent of itself, which would be that. This big old bulky base does not have the physical possibility of accessing this hydrogen. Sorry, this hydrogen, the one that's circled on the left. Because this hydrogen is secondary. It's on a carbon that's bonded to two other carbons, so that hydrogen is secondary. This hydrogen is bonded to only one, bonded to a carbon that's bonded to only one other carbon, and so this one is primary. And so this hydrogen is more accessible to this fat base than this other hydrogen. And so what happens is the base says, well, I'm lazy, I'm just going to grab the first hydrogen I come across, which will be the one that's kind of sticking out on the edges of the molecule rather than being buried deep inside the molecule. The steric constraints of having a giant bulky group like this say, I'm going to grab this one and give you this product as the major product. That should be ethyl, CH3, CH2, right? Now the Hofmann product, sorry, 1F, 2 N's. I always mess it up. I don't know why. It just seems weird for me. Hofmann. Now the Hofmann product is the major product, because the major product is the one that happens, that gets formed in the greatest concentration, which because of the size of the base means it necessarily is this. The Zaitsev product is still the same product as before, whereas where you remove this proton, electron snaps down here, and you get this structure. Right? But now the Zaitsev product is the minor product, right? So it's not necessarily the case that Zaitsev equals major and Hofmann equals minor. That's what we've been assuming up until now, but now that we know about Hofmann products, we have to think about, now we know about Hofmann products, we have to think about what is the conditions of the reaction. What type of base is it? What type of mechanism will that be? And therefore, what will the identity of the product be? So we kind of have this little decision tree to make, right? So we say, is it doing elimination chemistry? Meaning, do we have a base and we have heat as opposed to substitution chemistry? If the answer is yes, now we have two options, right? We can do E1 or we can do E2, right? How do we know which one we're going to do? Do we have a better leaving group, or do we have a better base, right? Again, this is the apples to oranges condition, because, or apples to oranges comparison, because we're comparing the basicity of one molecule versus the leaving group of another molecule. So it's like two different things. If the base is better, right, so suppose we say, oh, we have a strong base, it's got a negative charge. Then we have to do one more consideration, and we have to say, is the base bulky? Is it a fat guy? Right, so we have one other, that's an ugly arrow. Right, if the answer is yes, then Hofmann is major. And the answer is no, meaning the base is small, then Zaitsev is major. And if it's E1 chemistry, then Hofmann and we'll get the Zaitsev product, although it doesn't necessarily matter. There's not a direct correlation, I don't think. You just get the most stable product because the basicity doesn't have an impact anymore, because the rate determining step is determined by the leaving group leaving rather than the base doing his thing. Okay, so hopefully this little decision tree helps you out. So first you decide, are you indeed doing elimination chemistry, i.e. are you doing under heating conditions? Are you doing under basic conditions? And you have, a leaving group or a substrate that's facilitated to allow you to have elimination chemistry in the first place, right? So let's do a quick example, right? Suppose I gave you this, and I said NaOTBU, so sodium butoxide, and a solvent of HOTBU, which is T-butanol. And I say, give me the product. You should realize, if we go to our decision tree, say, do I have a strong, go up a little bit higher. Am I doing elimination chemistry? Yes, because I have a strong base. So that's yes. Is it E1 or E2? Do I have a better leaving group or a better base? Well, T-butoxide is a pretty good base. Bromine's a pretty good leaving group, but T-butoxide is a better base than bromine is a leaving group. So we'll do E2 chemistry. Is the base bulky? Yes, it's a fat guy. And so we're expecting to get the Hofmann product as the major product. That would be major. Hofmann. This would be Zaitsev, which would be minor. So Hof and major. Zaitsev and minor. Okay. A good thing I like to ask is I like to do stuff like this. I like to say, why is this? Okay. NBS, HV, gives you some product and you guys have to fill in the box. And then I have to say HOET and heat, and then give me the product of that, and this will be major, right? I love structuring questions like this. You say, well, what's this first step? If I had NBS and light and I add it to this molecule, what do I necessarily have to get? By a factor of 19,400, I get that. And then I identify that I'm doing elimination chemistry. Is this a strong base or a weak base? It's a neutral molecule, and so I say, oh, it's a weak base. So weak base, elimination chemistry, I should get the Zaitsev product. Get that. That on our decision chart, that will be here, right? Yes, we're doing elimination chemistry, good leaving group, weak base, therefore Zaitsev, right? So I love to structure questions like that. I'll do one more, and then I'll call it a day. This is actually the same example from lecture. So I'll start with the brominated product. And I'm going to give you potassium methoxide, KOCH3, and the solvent will be methanol, which instead of drawing it that way, I'm going to write CH3OH. And I want the major product. So the major product will say we have a strong base because we have methoxide. Even to be more explicit, I would do that. The major elimination product would be the most substituted alkene. So if we go up to our decision tree, elimination chemistry, yes, because we have heat, E1 versus E2, better leaving group, better base, while methoxide, ethoxide, T-butoxide, those are good bases, a little bit better than the leaving groups, since these leaving groups are not resonance stabilized or anything like that. The oxides, the carbon oxides, are better bases. Is the base bulky? No, it is not, so we should get the Zaitsev product as the major product. And so which proton are we going to remove? We should remove this proton right here. So this grabs, I'll draw it. That goes there, that snaps down, bromine kicks out, we get our major product. Is this molecule capable of getting the anti-periplanar conformation? Yes, because this bond has free rotation. This hydrogen can be in any orientation relative to the bromine. We can spin it around. There are no stereochemical relationships that prevent this from happening, or no steric relationships either. Alright, so that's the end of chapter 7. We have our exam on the Monday after spring break, in case you were unaware. It will cover chapters 5, 6, and 7. I will be making a quiz for you guys today or tomorrow about, it'll hopefully help you study for exam 2. Maybe it'll be some complete the reaction, it'll be some dehydration, it'll be, stuff like that. It's 10 points, turn it in on the day of the exam. I also made a study guide, or what I'm going to call a study list. So it's a list of things that you should be able to understand, as well as a list of things you should be able to do. That was just basically for your studying purposes only. There's no points associated with it or anything. You just use it to help you study. You should have done all the homework by now. If not, make sure you finish chapter 7 homework problems, the required ones, which are due on the day of the exam when we get back after spring break. And you should also be doing the recommended problems, right? So this is really where the effort starts to get ramped up, guys, because if you don't understand SN1, SN2, E1, E2 because you didn't study enough or you're just not sure or whatever, you're really going to struggle with chapters 8, 9, 10, 11, 12, and even 13, which is the end of OChem 1, because we're going to take our alkenes that we just made in chapter 7, and we're going to start adding things to them to make them more complex. So we're going to learn an entire new reaction type. So we already have to know the previous ones so we can build on top of it. It gets much more logically dependent from here on out. I know chapters 1 through 4 or even 1 through 5 kind of seem disjointed from each other, but here on out, chapter 6 is dependent on 5, and 7 is dependent on 6, and 8 is dependent on 7, and it gets a lot tougher. So if you've been kind of cruising because you're getting it in lecture and you do some homework and you get it and you're doing all right, points-wise in class, that's good, but don't slack off because it's going to get more difficult. So, all right, good luck. Have a good break, guys. I will see you in a couple weeks. If you have questions, whatever, feel free to email me. You know me, I'm always answering my emails. So, and send it to my email address, jursic.sec@gmail.com. Don't use the Canvas messaging system. That's garbage. I hate Canvas. So, all right, good luck, guys. See ya.